So we start by defining trivial covering projection. So trivial covering projection is nothing but a projection map. So you can think of it as a projection map, and this projects onto S, where this is discrete. So this D is discrete. So let us quickly draw an example. So say we have a circle S1 here, and we want to give its trivial covering projection. So we are just going to draw a trivial covering projections like this. So these are a bunch of circles. So say this circle we will write as S1 times 0 and similarly you go on the top. So we have made a trivial covering projection of a circle. So this is the trivial covering projection. Now we come and talk about covering projection. So again, the covering projection is a map. Now we are talking about this map P. Now this map P is continuous map, and it is locally, so P is a continuous map, and locally it is a trivial covering projection. So this B we call as the base space. So say B has a cover, so this is the cover of B. So locally this looks just like this. So we are going to copy this right here. So I have just replaced S with U alpha, and the only thing is that now you add P inverse of U alpha here, and this phi alpha is a continuous map for each alpha. So we are working through the index of the open cover. So locally this will look precisely like the map above. This D alpha is discrete. And we also have this extra condition with P inverse of U alpha. So let us see this now with an example. So now we are going to draw a covering projection. So again we will stick with the example of a circle. So say we have a circle right here, S1, and then let us draw its projection. So we have this, and now we can see for an open set here. So say you have open set U alpha. So this set is carried all the way up. So let us say it is carried right here. So now you can say I will name this U. So you have say U times 0 here. This portion is U times -1, U times -2, so on, U times 1, U times 2, and so on. So this is the standard mapping from real lines to S1, and I will write down the standard mapping in a minute. So you can see that locally this is just exactly like this side. So these two are the same locally. So that is the point. Now another thing is evenly covered in the definition. Now in this evenly covered, you talk about a subset of the base space. So subset U of the base space B is evenly covered. So instead of U alpha above, we are just replacing U alpha above with U. So example, we have already drawn this from real numbers to the circle. You have P as a continuous map, so that is basically T from here gets mapped to exponential of 2 pi I t, and the inverse map of an open set is u times integers, which I have just written here. Notice that the standard cover of S1, you can say it is of union of two open sets. So this set you can say is S1 minus 1, and U2 could be S1 minus 1. In fact, you could take any 2 points P and Q and form an open cover. Now here I have just drawn a small open set U. Now we want to talk about the Lebesgue covering theorem. So say X is some compact space and it has an open cover. So then there exists an epsilon greater than 0, and this epsilon we will call a Lebesgue number, such that for every X in this big space X, there is a ball around it, the ball around point X, such that it is contained in this cover U alpha. So let me just draw this. So say you have the space X, and this space is covered by some cover. So this is, say, cover of the space. And you have some point X in the space here. Then you can always form a ball around it, and this ball is contained within some U alpha it is contained in. For example, this ball, we drawn a ball around it, it is contained in this U alpha. It could also lie in the intersection. So basically we just want to talk about a Lebesgue number, and this number we need because we are going to use this number for proof of homotopy lifting property. So it's the proof is kind of standard analysis proof. So what you do essentially is you first think of X as a subset of Rn, that it is a closed and a bounded subset of Rn. So if it is a closed and bounded subset of Rn, you obviously want to use a finite cover here. So you want to use Heine-Borel theorem and say it has a finite subcover. So let us start with this. So what we do is for every point X in the space, so what you do is basically for each X in the space, you pick a ball. Yeah, you pick a epsilon X. So for every for each X in the big space X, you pick up this epsilon X, and you pick up this epsilon X so that B of X comma 2 epsilon X lies in U of alpha. So this is one thing. So step 1 is this: you pick 2 epsilon X. This we are going to use later. Also, you can see that, you know, if you take all the balls around all the points, then you form the open cover of the entire space. So this is the open cover. So now in open cover, notice that I am using epsilon subscript X. So this is separate from this. So essentially around each point we have 2 balls of different radii. So one is 2 epsilon X, which we will use on later on, and one is just epsilon X. Now you have an open cover. Since X is compact, this cover is finite. So you have just picked a finite number of balls which will cover the entire space X. Now you just pick the minimum epsilon. So we have all these epsilons here. There's one epsilon here, a bunch of epsilons here, and one epsilon here. So you pick up the minimum of all these epsilons. Now for any point y in the space X, so again this is a space X, so for any point y lying in the space X, now y will lie in some ball here. So say the ball has index k, so y lies in some ball. Yeah, so if y lies in this ball, this implies that you can also form a ball around point y with the minimum radius. So if you form this ball around point y, so this epsilon here is less than epsilon subscript x of k, because this epsilon is the minimum. So this ball will lie in this ball, but this ball will further lie in a ball with radius twice epsilon k. So notice that I'm using twice epsilon k now. So the idea is simple. You have point y, you have ball 1 here, which has the radius epsilon k. This lies in the bigger ball with radius twice epsilon k, and obviously there is a ball inside it, which is this ball epsilon, and this lies in u of alpha. We're just copying this right here. This lies in u of alpha. So we wanted to show this for all x element of x, b x comma epsilon lies in u alpha. So instead of x, we are now writing for all y and x, you have by of y comma epsilon lies in u of alpha by this entire chain. So you have by comma epsilon lies in u of alpha. So we have just shown the result. So we are just using this statement instead of the above one. And that is it.